In today's video, we're going to look at graphs of functions and what the graph of a function would look like, and then in particular, we're going to look at their domains and ranges dependent on the graph, and then we're going to look at different functions that are well-known functions, and we're going to see what their graphs look like so that you can immediately pick them out from a picture of a graph. So to start with, this is bringing it back to what we did in our first homework. When we graph a function, we know already for the definition of a function that we cannot have an x-coordinate that has two different y-coordinates associated with it. So we can't have two different function values for any given value x. So in our first homework, we looked at something called the vertical line test. That said that when we graphed a function, if at any point on that graph we could draw a vertical line such that it went through two different y values for any given x value, we knew that that graph did not actually represent a function. The vertical line test tells us that if you draw a vertical line anywhere across your x-axis, that you should only cross at most one point on your graph. Okay, so for example, if I go ahead and I draw this graph. Okay, so I've got my x-axis and my y-axis. Okay. This does not represent a function because I can draw a vertical line at some point on my x-axis and I cross two different points on my graph. That tells me that this graph does not represent a function. As it doesn't pass the vertical line test. Okay. Now, as we said, this is because for some x value, it doesn't matter for how many x values, as long as this is the case for at least one x value. If you get two or more different y values for a given x value, you therefore know that it is not a function. It does not pass the vertical line test. So for each x value, we should have only one y value. Okay. An example of a graph of a function that does pass the vertical line test is the quadratic curve. The graph of y is equal to x squared. Okay. This does pass the vertical line test because anywhere on my x-axis I can put a vertical line through my x-axis and I only cross one point in the graph, telling me that for each x value I only have one given y value, one function value. Now we need to look at domains and ranges given a graph. Okay. I'm going to actually start with y is equal to x squared when we're looking at domains and ranges. Okay. So I'm going to redraw my quadratic graph. So y is equal to x squared. Just a quick sketch of it. Now, this graph of y is equal to x squared. Okay. It goes off and upwards in both directions infinitely. Okay, so to the left it goes off infinitely towards negative infinity, and to the right it goes off towards positive infinity. So if I take x as any real number, I can always square it and I get another real number. Okay, you can do that for any x up to infinity and all the way down to negative infinity. So that tells me that my domain is all real numbers, or in set notation is negative infinity up to infinity. Okay, because I can square any real number that I like. Now the question is, what is the range for this function? Okay. Well, if I square any real number, positive or negative, I always get a positive number back. For example, if I square -3, I get 9. I don't get -9, I get +9. If I square 0, I get 0. That's the lowest value that I get as a y value whenever I square any number. Okay? Any other number, positive or negative, is going to give me a value greater than 0. So the lowest value that I can actually obtain from squaring a number is 0. I can go all the way up to infinity. Okay? If I square a very, very large number, I'm going to get an even larger number back out of that. So my range is 0 all the way up to infinity, but I have to include 0 because if I square 0, I get 0. So that's why I've put a square bracket around 0, and then we go all the way up to infinity. That agrees with my graph here. Okay? We can see from the graph of y is equal to x squared that the lowest value that I can have for y is 0. I can't go negative. Okay, I never get a negative y value back. I always get a positive y value. So it tells me that my domain is all real numbers because I can square any real number, but my range is then 0 up to infinity because I always get a positive value back. We're going to do a couple other examples. And these are just sketches of graphs. So bear with me while I draw these. Okay, I have this graph of a function. I want to look at what my domain and range of this particular function is. Domain means I look at the x coordinates, range means I look at the y coordinates or the f of x values. Okay, where this is my x and y axes. My domain here is the set of x values. So my lowest x value that I have is -4. The largest x value that I have is 5, and I'm including those two numbers. So my domain is -4 up to 5, including those values, so we use square brackets. My range is all possible y values, so all possible function values that I get back when I plug in an x. So if we look at this, what is my lowest y value and my highest y value? Well, my lowest y value is going to be -3, and the largest y value that I actually get it twice from both of these x coordinates. I get 1. So my lowest value is -3, my largest value is 1, and I include both those numbers. Here you see that you actually have endpoints. So this particular function, it starts at x is equal to -4 and only goes up to x is equal to 5. So we've restricted the domain. There are cases like that y is equal to x squared graph where you may have an unrestricted domain. So we're going to do another example. Where this time I have a horizontal line between x is -5 and x is 4, And then I have this line that then shoots off towards infinity after that x is equal to 4 value. So when x is greater than 4, we're going to get a larger and larger and larger y value. So let's look at our domain and range in this case. Our domain, well, the lowest x value that we have is -5. The largest x value that we have, well, here, because we have an arrow on the end of the line, that tells me that it goes off infinitely. So whenever you see an arrow on the end of a line, it tells me that it goes off in that direction infinitely. Whenever you end up with these endpoints where you've just got a dot at the end, tells me that that is an endpoint. That's as far as you go. So that tells me that my largest x value, it goes off infinitely, so it's infinity. Now, my range, again, we look at the smallest and largest y values possible. Well, I have this horizontal line that is as low as I can go here. So my range starts at -1 and we include that value. But again, it goes off infinitely in the positive infinity direction. So our range is -1 up to infinity. So what I want you to see here is whenever you have an arrow at the end of a line, it tells me that this thing goes off infinitely. Whenever you have just a circle at the end of a line like this, then it means that it's an end point of a line and you don't go any further than that. Something else that I want you to be aware of is looking at independent and dependent variables. Okay. Whenever we say that we have f of x, okay, that is the function value at x. Okay, it's a function of x. X is an independent variable. Okay. X can be whatever it wants in the domain. It's not dependent on anything else. Okay. Examples of an independent variable are things like time and maybe weight, okay? Then you have f of x, a function of x. Whatever value that you get out is going to be dependent on the value that you put in. So f of x, or y, depending on how you want to actually write it, is the dependent variable. Okay, because x can equal whatever it likes in the domain, and then the function value, f of x or y, depending on how you want to put it, is going to depend on that value of x that you input. Examples of dependent variables are things like speed or cost. Okay, so I'm going to do a couple examples here, but we will write this down. So independent variables are things like time and weight. And then dependent variables are things like speed, cost, etc. Okay. If you think about it, when you see graphs of things in word problems and that kind of thing and functions, you always have speed as a function of time. So how fast are you going at a particular time? Or you could have, we'll do a particular example with cost of mailing something. Depending on the weight of the thing that you are mailing will depend on how much it costs. Another example you could have is height as a function of time. So as time goes on, how tall is a person? Let's go ahead and actually draw a graph for that. So, for example, we can have height as a function of time. Okay. So time is my independent variable, and height would be my dependent variable. Okay, so as time goes on, How tall is a person? So when you're a child and you grow up, you obviously grow at a steady rate, and at some point you then reach a height that you are for the rest of your life. So if we look at that in terms of time and in a graph, you would see that you would get this steady growth as you were growing up as a child and a teenager, and then your height would eventually level off. Okay, so just roughly that would be a graph of height as a function of time. We could also look at a graph for the cost of mailing a letter according to its weight. Okay, now for this one, and this is something else that I want to talk about in terms of graphs. Okay. The cost would depend on the weight. So the weight would be your independent variable. The weight of a letter is what it is. And then the cost of mailing it will depend on that weight. Now you tend to find that this will go up in increments. So for a letter that has a weight between a certain number and a certain number, there is a certain cost. Okay, and then there'll be a next level up, so that between another weight and another weight, you'll get another cost. So the way that we will actually draw that is like this. This is something called a piecewise function. Okay, so we also see that we have these open circles. That is because once you reach that weight, you have to go up to the next level. So at that particular weight, whatever this weight is, we are no longer at this cost, we are now at this cost. But I can't have two different y values for that one x value. That doesn't represent a function. So therefore I put an open circle where I am no longer at that particular cost, and I put a closed circle meaning I am now at that cost for that particular x value, for that particular weight. So if you are undefined at a particular point on that line, you put an open circle. And then at the next point where you are defined, you put a closed circle. Okay? So that is why we do that. I now want to look at the definitions of increasing, decreasing, and constant for a particular graph. Okay. When is a function increasing? When is a function decreasing? And when is it constant? Well, we always say that they are increasing, decreasing, or constant over a particular interval. We don't say that it's increasing for the whole graph. We don't say that it's decreasing for the whole graph. We always say that it is on a certain open interval, and therefore it is increasing on that interval. It's just a way of looking at local increase and decrease. So we say that a function is increasing on the interval AB. Okay, this is for x values. So we are looking particular at x values. Don't look at y values right now, the function values. We are looking at the x values. So it is increasing on this interval of x values if for any x1 and x2 which exists in this interval. So for any x1 and x2 that are in that interval, you find that the function value of x1 is less than the function value of x2, where x1 is less than x2. What does that tell me? Okay, this tells me that for this given interval, if I pick any two x values where one's less than the other, so I've got two distinct x values where x1 is less than x2, I will always find that if x1 is less than x2, then the function value of x1 is less than the function value of x2. So for any two x values that I want to pick in that interval, such that one's less than the other, then I will find that the function value of the first one is always less than the function value of the second one. Okay. Kind of makes sense. If we were to go ahead, you can just do this with a straight line graph, like this. Okay. Then take your open interval, let's say to be A and B. Okay. I can pick any x1 and x2 in here. Okay, where x1 is less than x2, that's obvious from our x-axis that x1 is less than x2 here. They both land in my interval, but x1 is less than x2. And I find that if I then look at their function values here and here, so this would be f of x1 and this would be f of x2, because that's where, if we were to plot this out, okay, we see that f of x1 is less than f of x2. Okay, I can do that for any x1 and x2 in my interval. That tells me that this function is increasing, which when we look at the graph, that makes sense. It is increasing between A and B. It's actually increasing on a larger interval than that in this case, but we can definitely see that on this open interval AB, that if I were to pick any x1 and x2, such that x1 is less than x2, then f of x1 would be less than f of x2. Okay. In a similar way, we can look at decreasing. So when is a function decreasing on an interval? So a function is decreasing on the interval A, B, if, okay, same thing again, this time we're going to take x1 and x2 which exist in AB, so I've taken two x values that are in my open interval AB such that x1 is less than x2, so same as last time. Okay. Then I should find that if it is decreasing on that interval, that f of x1 is greater than f of x2. Again, I'm going to do this for a straight line graph, just so we can see how this works. So if I take A to be here and B to be here, x1 here, x2 here, so x1 is less than x2. Then if I look at the function values, so if I plot this out, okay, I have f of x2 is here and f of x1 is here. Okay, I can see that now x1 is less than x2, but f of x1 is greater than f of x2. That tells me that if I can do this for any x1 and x2 in that interval AB, such that x1 is less than x2, and I find that the function value of x1 ends up being greater than the function value of x2, and that happens for all x1 and x2 that satisfy these properties, then I have a decreasing function on that interval. Again, we can see this from our line, okay? It decreases, your function value decreases as x increases. What about a constant function? What does that look like? And that is literally going to be this horizontal line, like that, okay? And again, you say that you've got this open interval AB, so the function is constant on AB if for x1 and x2 that again exist in that open interval where x1 is less than x2, then f of x1 is going to be equal to f of x2. Okay, again, we'll look at it here. Let's say I've got my value A here, my value B here. and then I take x1 to be here, x2 to be here, so x1 is less than x2, and I find this time that their function values are exactly the same. Okay. F of x1 will equal f of x2, so we have a constant function on that open interval. I'm going to do a sketch of a graph here, and we're going to look at the intervals on which the graph is increasing, decreasing, and constant. Okay. So this is going to be my graph, and I'm going to put on the points that we have. Okay, so these are our notable points. And I want to look at on what intervals is this increasing, decreasing, and constant. So the intervals that we always give are going to be the x values, not the y values. I'm looking at for what x values is this function increasing. So for my given x values, I always find that my y values or my f of x values are increasing. And again, for a particular set of x values, where are my function values decreasing, and then where are they constant? So I always give the x values, and I do this in set notation. Okay, so if we look, where is this function increasing? Well, I can see that my function is increasing here. Okay, it's increasing on a curve, but it is increasing. Okay, where else is my function increasing? Well, I'm decreasing all the way from -3 all the way down to 2 here. And then again, I start to increase. Okay, so wherever the blue is where we are increasing. So I am increasing between x is -5 and x is -3. And then I'm also increasing between x is 2 and x is 5. We always do these as open intervals, reason being that the points where you go from increasing to decreasing or decreasing to increasing, they are called turning points because you are turning from increasing to decreasing or decreasing to increasing or maybe increasing to constant, etc. So wherever you change direction, we always call those turning points. So we don't include those points in our set notation. So where are we increasing? For what x values are we increasing? Okay. Well, we're increasing between x is -5 and x is -3. We don't include those points because at those particular x values, we have those turning points where we go from constant to increasing and from increasing to decreasing. Then union with, we are also increasing between 2 and 5, where x is 2 and x is 5. Again, not including those points because one of those is a turning point, the other one is an end point. We don't include an end point in our set notation. Okay. Now let's look at decreasing. Where am I decreasing in this function? So I'm going to do this in green. So I'm decreasing between x is -3 all the way down through there, up to x is equal to 2. So I'm decreasing between -3 and 2. I go through the x-axis at x is equal to -1, but I'm still decreasing. I'm still decreasing all the way to x is equal to 2. So I don't actually count that right now as a turning point. I'm decreasing all the way from x is -3 to x is 2. And how about constant? Well, I'm constant on this horizontal line here. So I'm constant between x is -7 and x is -5.